one-to-one functions and their inverses. First, let's discuss one-to-one functions. We know that a function is an operation that takes every element of a domain to exactly one element of a range. To be a one-to-one function, the reverse must be true as well. So that means that every element in the range can only come from a single element in the domain. So this function that you're looking at here is a one-to-one function because every one x value goes to exactly one y value. And you can see that happens for all four of these numbers here. The other diagram represents something that is not one-to-one. And the main reason for this is because the number 3 gets assigned to the number 4, but the number 2 also gets assigned to the number 4. So if I asked you, where does 4 come from? You have two possible answers for that. And to be a one-to-one function, this number 4 can only come from one input value, not two. So this is a fairly rudimentary and fundamental way to view one-to-one functions. Now let's go to a formal definition. So the definition of a one-to-one function says that a function with a domain A is called a one-to-one function if no two elements of that domain A have the same image. So in other words, f of x1 cannot be equal to f of x2 anytime x1 and x2 are different. An easier way to determine whether a function is one-to-one is by something called the horizontal line test. So if you have the graph of a function, the function is one-to-one if and only if no horizontal line intersects its graph more than once. So for example, if you consider the graph here of some function y equals f of x, this graph does not represent a one-to-one function because the horizontal line you see right here hits the graph twice. And because it hits the graph twice, it violates the definition of a one-to-one function. Here we have x1 and x2, and those x values are not equal to each other. However, f of x1 and f of x2 are equal to each other. So now let's consider the function f of x equals x cubed. Is this a one-to-one function? The answer is quite simply yes, because every possible horizontal line that you could draw is only going to intersect this graph at the most one time, right? It's never going to hit more than once. Now, another way to think about this is if x1 is not the same as x2, then f of x1, which would be x1 cubed, would not be the same as x2 cubed, which would be f of x2, right? Because if two numbers are different, when you cube those numbers, you get different values. So this is a more algebraic way to understand why it is one-to-one. But again, the horizontal line test is the easiest way to determine this. In the next example, consider the function g of x equals x squared. Is this one-to-one? Clearly the answer is no. You can see that when we draw a horizontal line here, we intersect the graph more than once. In fact, any horizontal line you draw above the x-axis is going to intersect the graph more than once. Algebraically, the reason this happens is because I can give you an example of two x values that are different. For example, x1 equals 2 and x2 equals negative 2. However, f of 2 is 2 squared, which is 4, and f of negative 2 is negative 2 squared, which is also 4. And so here we have equal y values for two different x values. And this violates the definition of a one-to-one function. Now this function g of x equals x squared can be modified to turn it into a one-to-one function. Basically what we would need to do here, we'll define a new function. We'll call it h of x equals x squared. But then we're going to restrict the values of x to only be non-negative values of x. So in essence, what we're doing here is we are erasing the other half of the parabola here, because we are saying you're only allowed to plug in positive x values, right? So now we only have one side of the graph, and now every horizontal line you draw only intersects the graph one time, which means this would actually be a one-to-one function. So even functions that are not one-to-one, they can sometimes be made to be one-to-one by simply modifying the domain of the function. In our next example, we are going to show that the function f of x equals 3x plus 4 is one-to-one. Now, fundamentally, we should know that this is a one-to-one function because the graph of 3x plus 4 is a line. It's going to look something like this. And then you can imagine that any possible horizontal line that you would draw would only intersect that graph one time. So we can get a sense that it passes the horizontal line test. But can we show that it's one-to-one algebraically? So what I'm going to do is assume that f of x1 is equal to f of x2. Now, f of x1 would simply be 3 times x1 plus 4, and f of x2 would be 3 times x2 plus 4. Now, if that's true, notice that if I subtract 4 from both sides, we end up getting 3x1 must be equal to 3x2. And then if we divide both sides by 3, we end up getting x1 is equal to x2. So if we assume that two function values are equal, this forces the x values to also be equal. This means that it must be one-to-one. Now let's define an inverse of a function. And I'll go to the picture down below first. We know that a function takes a value in a domain and it applies some rule to that value and it sends it to a new value in the range. The inverse of that function is just going to take the value here in the range and it's going to send it back to where that value came from. So an inverse of a function is simply a way to invert the process of the function. So it's a way of switching. So let f be a one-to-one function with domain A and range B. The inverse function, which is denoted f with a little -1 here, has domain B and range A, and is defined by f inverse of y is equal to x anytime f of x is equal to y. So again, you're just switching the x's and y's. So in the next example, we would like to find f inverse for specific values. And notice the way I said this. I said f inverse. I didn't say f -1, right? We call this the inverse of f. So if we know that f of 1 equals 5, so here's a picture of that. F of 3 is equal to 7, here's a picture of that. And f of 8 is equal to -10, then let's find f inverse of 5, f inverse of 7, and f inverse of -10. So basically, we're just switching the process. So we know that the function is what takes these values over to these values. The inverse function is going to take the values over here back to where they came from. So f inverse applied to the number 5 is going to take 5 back to the number 1. F inverse of 7 is going to be 3, and f inverse of -10 will be +8. So because we know that f takes these values to these values, we know the inverse is just going to take these values back to where they came from. In the next example, we are going to find values of an inverse function once again. So in this example, we have two different functions. We have a function h, which is represented by this table, and we have a function f, which is represented by this graph. So what I want you to notice here is that the function h takes these numbers and sends them over to these numbers. So for example, I could say h of 2 is equal to 5. I could say h of 3 is equal to 8. The inverse function is just going to go the other way. So it's going to take these function values back to where they came from. So for example, I can say h inverse of 8 is equal to 3, or h inverse of 1 is equal to 5, right? So if you have a table, you can determine the inverse values of those values in that table. And the same is true for the graph that you see here. So this graph here tells you that if you take the function f and you apply it to the number 4, you will get the y value equal to 3. And if you take the function f and apply it to the number 7, you will get the y value equal to 5. So the inverse function is going to be applied to the y values, and it will take you back to these x values. So for example, f inverse of 5 must be 7, and f inverse of 3 must be 4. The inverse function property says let f be a one-to-one function with domain A and range B. The inverse function f inverse satisfies the following cancellation properties. F inverse of f of x is equal to x, and f of f inverse of x is equal to x. So any function f inverse that satisfies these conditions must be the inverse function of f. So the inverse function is the function that cancels out the original function. And likewise, the original function cancels out the inverse function. And this should make sense, right? If you just think about your diagram, if I have a number x, the function is going to send that to a new number y, and then the inverse function is going to send that number y back to x. So if I apply the inverse function to the original function of x, we are just going to get x, right? In other words, they cancel each other out. So in this next example, we would like to verify that two functions are actually inverses of each other. So in this case, we have f of x is equal to x cubed, and g of x is equal to x to the 1/3. To verify that they're inverses, we have to do f of g of x, and we have to do g of f of x. So f of g of x is going to be taking g of x and plugging it into f of x. So that's going to be f of x to the 1/3. And when you plug x to the 1/3 in here, you get x to the 1/3 to the 3rd. And of course, this is x to the 1 because we multiply these powers together, and this is equal to x. G of f of x is going to be g of x cubed, because f of x is x cubed. And this means we're plugging x cubed into here. So this becomes x cubed to the 1/3, and for the same reason, this turns into x to the 1, which is equal to x. Since we get x for both of these compositions, this means that g of x is equal to the inverse of f of x. Now let's talk about how to find the inverse of a one-to-one function. So there are basically 3 steps. In the first step, we're going to write y equals f of x. So if you're given some f of x, you're just going to replace f of x with the variable y. And then you're going to solve this equation for x in terms of y, if this is algebraically possible. And then finally, we will interchange x and y, and the resulting equation is your inverse. So let's consider the following example. I would like to find the inverse of the function f of x equals 3x minus 2. So in step 1, I'm going to change f of x to y. Y equals 3x minus 2. In step 2, we're going to solve for x. So to solve for x in this equation, we're going to add 2 to both sides. And this gives us y plus 2 is equal to 3x. And then I'm going to divide by 3 on both sides. And this gives us y plus 2 over 3 is equal to x. And then in step 3, we're going to interchange x and y. So in this equation down here, x becomes y and y becomes x. So we have y equals x plus 2 divided by 3. And this new y is your f inverse. So the inverse function of f of x equals 3x minus 2 is f inverse of x equals x plus 2 divided by 3. So let's go ahead and go through this process again. So let's find the inverse of this function. First, we're going to change f of x to the variable y. Second, we're going to solve for x. So to solve for x here, I'm going to multiply both sides by 2. This is going to give us 2y is equal to x to the 5th minus 3, right? Because these 2's cancel out here. Then let's add 3 to both sides. This gives us 2y plus 3 is equal to x to the 5th. And finally, to solve for x, we're going to take the 5th root of both sides. So we get the 5th root of 2y plus 3 is equal to x. And then in our third step, this x here becomes y. And on the other side, the y becomes x. And this is our inverse function. So the only thing left to do is to change the name to be f inverse of x. Let's do this process one more time. Let's find the inverse of the following rational function. This is going to be a little bit more challenging because there's more than one occurrence of the variable x. So let's go ahead and go through this. First, we'll change f of x to be the variable y. And then in the second step, we're going to solve for x. Now at first, this is maybe not obvious in terms of how you're going to do this. So what I'm going to do here is multiply both sides by x minus 1. So on the left-hand side, we get x times y minus 1 times y. So we're just going to distribute there. And on the right-hand side, we just get 2x plus 3. Now, to solve for x, I need all the terms with the x's. So this term here and this term here. I need those on the same side of the equation. So I'm going to subtract 2x over here. And I'm going to add y over there. So that's going to give us xy minus 2x is equal to y plus 3. Now, why did I do that? Well, the whole point of getting the x's on the same side of the equation is now I can factor out that x. So this becomes x multiplied by y minus 2 is equal to y plus 3. And now I can just divide both sides by y minus 2. And that gives us x equals y plus 3 over y minus 2. And this is pretty much our inverse. Last step, we're going to interchange x and y. So we get y equals x plus 3 over x minus 2. And my final step is now I'm just going to rename this function f inverse of x. Inverses of functions and the original function have a nice graphical relationship. So keep in mind that an inverse function just interchanges the x and y coordinates, right? So if x equals a and y equals b on the function, then on the inverse function, x is going to be b and y is going to be a. And those 2 points are always symmetrical across the line y equals x. So what this means is that if we have some graph of some function f, like the one you see here, the graph of the inverse is going to be a mirror image of that graph across this line y equals x. So in this next example, let's sketch the graph of f of x equals x minus 2, and then we'll use that graph to sketch the graph of f inverse. And then finally, we'll find the equation for f inverse. So for the graph, this is not terribly difficult. We should know that y equals the square root of x, is one of our special graphs, and it looks something like this. And so the square root of x minus 2 is just going to be a horizontal translation of that graph 2 units to the right. And so that graph is going to look something like this. Let's make this look a little cleaner. So now, what is the graph of the inverse going to look like? Well, let's remember that the line y equals x is this line right here. And so the inverse has to be a mirror image across that line. So let's just take a couple of points here. This point is the point 2, 0. So on the inverse function, we're going to have the point 0, 2. And let's pick another point. This point here appears to be the point 6, 2. So then the point 2, 6 should be on the other graph. And if I connect those in a way that makes this look like a mirror image of the other graph, we can see that the inverse should look something like this. Now let's bring in a nice picture. All right, so there is the graph of f and also the graph of f inverse. Now let's find an equation for f inverse. So let's keep in mind the original equation was y equals the square root of x minus 2. So in step number 1, we're going to call this y instead of f of x, which is what I've already done here. And now in the second step, we're going to solve for x. So to solve for x, we're going to take this equation and we're going to square both sides. This is going to give us y squared is equal to x minus 2. Then we can add 2 to both sides. And this is y squared plus 2 is equal to x. And finally, in the last step, we're going to interchange x and y. So we get y equals x squared plus 2. Now you have to be really careful here because y equals x squared plus 2 is actually a parabola that looks like this. But you can see up here on the graph that we are not getting this side of the parabola, right? Because the original function only has this piece, and so the mirror image is only that piece, not this part here. So what's going on? How come we're getting the whole parabola here? Well, it's because we're not taking into account the fact that there is a restriction on the domain of our original function. So for the function square root of x minus 2, the domain is x must be greater than or equal to 2, and the range is y must be greater than or equal to 0, right? And you can see that right here on the graph of the original function. You can only plug in numbers that are 2 or greater, and your y values are always going to be 0 or greater. So when you find your inverse function over here, remember the domain and the range are going to be switched because the inverse function switches the x's and y's. So the domain of your inverse is x must be greater than or equal to 0, and your range is going to be y greater than or equal to 2. So because your domain is only positive values for x, that means we're not going to include the other side of this. Now, we already knew that from a graphing standpoint, but the point is when you find the inverse of your function, you have to put the domain and range with it because otherwise you'd be getting this whole parabola, right? Which is not a part of the inverse function. And for our final example, at a local pizza parlor, the daily special is $12 for a plain cheese pizza plus $2 for each additional topping. Find a function f that models the price of a pizza with n toppings. Okay, so this isn't too bad. So let's let n equal the number of toppings. And so f of n, the price of the pizza, is going to be $12 plus $2 times the number of toppings. Now let's find the inverse of this function. So let's say that f of n equals p for price. So first thing I'm going to do is I'm going to change f of n to be p. And now what I'm going to do is I'm going to solve for n. So to solve for n, we're going to subtract 12 from both sides. This gives us p minus 12 equals 2n. And then we can divide by 2 on both sides, and that gives us n equals p minus 12 divided by 2. And then we would change n to be f inverse of p. And f inverse of p is going to be p minus 12 divided by 2. So what does this represent? Well, it represents the number of toppings that you get when you're given a certain price. So for example, in part C, if a pizza costs $22, how many toppings do you get? So f inverse of 22 is going to be 22 minus 12 divided by 2. This is 10 divided by 2, which is 5. So that means a pizza that costs $22 must have 5 toppings. And that concludes this video lesson.